Good afternoon, everybody. This is Professor Lemieux. Hope you're having a good day. Today we're going to start our discussion about frequency response and control systems. The chapter in your book is pretty extensive on this. However, I feel that the presentation jumps right into Bode plots, which is the tool that we're going to use predominantly for quantifying the frequency response of a system and the effect of adding a control system to that system. Before we jump into Bode plots, though, I think it's important to have some introduction to talk about really what the frequency response physically means and how do we get to a point where this Bode plot that is being described in so much detail in the book really comes from. So this is the purpose of this video. I hope you enjoy. Frequency response, we're going to define it here. It is the steady state system response to a sinusoidal input. Sinusoidal, tough word here, input. In contrast to what we've done before, which is to look at a system's response due to typically a step input, which is what we've primarily focused on so far in our discussion, right? And here, so the shape of the input, let's look at previous, and let's look at now. So before our input looked like this as a function of time, right? We had a system, and that system was going to see something like that. And now what we are seeing is our system, and our input is going to look like this. Etc. So in the previous case, traditionally, we had responses that did things like this if we had an underdamped second order system, etc. In the case of our new system, with this new input, I mean, it's the same system, sorry, but we're exciting it with a new type of input. What is the response? This is the question that we are trying to answer. Now, the word steady state here may mislead you a little bit, in that you're probably thinking, well, wait a minute, the input is constantly varying here, so how can the system behave in any sort of a steady state way? Well, what we mean by this is that the system is going to respond to this sinusoidal input in a manner that no longer changes with respect to time. So the behavior is necessarily most likely going to be cyclical, but from cycle to cycle there will be no change, and that's what we mean by steady state. Typically what's going to happen is in the early part of the excitation, when the system first gets excited by this sinusoidal input, then the system response might do a few funny things. We'll talk about this a little bit, and we'll see why they really don't matter for a certain, after a certain amount of time, and hence we're going to reach that steady state we're talking about. So another way to express this is that this frequency response is the response, the system behavior and again, I'm looking at a system, right, that's going to look like this. I got my input, which, as we said, now is different than it was before. I'm going to have my controller G sub C. I'm going to have my plant G. Output is C of T. Here's my sensor, okay, and my feedback loop, minus plus. I am looking at that system behavior of t, that's the output of the system, for r of t being sinusoidal, that means of the form a sine omega t. So this guy right there, that's the input frequency, which in this analysis, we're hitting the system with a constant frequency. That guy is a constant. So pick a omega, one value of omega, for your r of t, hit the system. What does this do to c of t at steady state? Pick a different omega, repeat what's the new response of c of t, etc. That's what the whole frequency response analysis consists of. So before we jump too far into this, let's do a quick little review of some of the important parameters that we're going to be dealing with. Given that we know that we're dealing with a sinusoidal input function, it is going to be important for block diagram and in our system transfer function analysis that we refresh ourselves a little bit as to what the Laplace transform of all this might be. So let's do a quick little review of Laplace transform here, and I send you back to your table 2.1 in your book so that you can look at it at the same time here. I'm simply going to write down the results without proof, but we've talked about this in the past. Recall table 2.1 or 2.2, I can never remember which one's which, where we look at the Laplace transform of various r of t's, and call this big R of S now. The Laplace transform is going to map us into the S domain, and specifically what we're looking at is a Laplace transform of something that looks like this sinusoidal input. So it's going to be a Laplace transform of a sine omega t, and from table 2.1/2.2 we see that that's equal to a times omega divided by s squared plus omega squared. Again, bear in mind that a and omega in this discussion are constant, right? S is our variable that we get from the Laplace transform. Let's call that equation 1. We'll come back to it back and forth as we move along. Okay. And interestingly, what are the roots of that transfer function? A omega over s squared plus omega squared. So let's take a note of that. So the roots are going to be what makes, or the poles are going to be the roots of the characteristic equation made by the denominator of this Laplace transform. So the roots of denominator, poles of the system, are s is equal to plus or minus j omega. Top of that, and we're going to see that that's kind of important as we move along, right? S is equal to plus or minus j omega, so that I could really also write this guy as a omega times s plus j omega times s minus j omega, and that have the exact same thing. So equation 1 is either of those two forms, okay? Similarly, to be complete, because sometimes the input is going to look a little bit different, our value of r, the input, could be some other function a times cos omega t, which is really the same as the sine one, it's just we're starting at a different place, right? But it's worth reviewing the Laplace transform of that as well as we're talking about this. And in that particular case, when r is equal to the cosine instead of the sine, then the Laplace transform of the cosine is as divided by s squared plus omega squared. So the numerator is what's different, so that the roots are also the same. In fact, let me just write that down so that we have that equivalency, right? Plus j omega, we said, s minus j omega. Okay, let's call that equation 2. Okay. Also, since we're going to be doing this, let me refresh you a little bit with something we talked about when we talked about the phasor / polar notation. Also recall because we've got these j's there. It's going to come in handy in a little while. The Euler's identity. A couple of weeks ago, I brought that up in class. Super important and practical result in these types of analysis, both for well, mostly for expressing the values of the functional relationship of our transfer functions in polar coordinates on the s-plane is what's going to be important. But in this particular context here as well, because we're dealing with sine and cosines, it's helpful to look at Euler's equation and isolate what that would be. So you can show yourself somewhat readily from Euler's equation that you can express the sine of any angle, theta, and of course that angle theta could be omega t, as e to the I theta minus e to the minus I theta. And here I notice I'm going back and forth between my i's and my j's here, but both of them represent the complex number square root of minus 1 divided by 2i. And similarly for cosine of theta, that's going to be e to the I theta plus e to the minus I theta divided by 2. So no imaginary number in the denominator. Let's call this guy equation 4, and this guy equation 5. Okay, all right, enough for the review here. This is stuff we've talked about before, but make a note of these 5 equations. We'll come back to them as we move along. So, you already know from your study of vibrations that you have already a background of a bit of an engineeringly intuitive feel for how systems respond to a sinusoidal input. You've seen in your vibe study that at some frequencies the amplitude of a system's response is vastly different than it is for the very same system at different frequencies, especially as you get close to the point of resonance of the system itself. So being able to quantify how a system is going to behave as the frequency varies is very important in order to make sure that the system remains stable, for example, and does not experience too many very large oscillations, let's say. Where is that important, this type of analysis? Well, there's all kinds of very, I think, obvious case in engineering where that would be the case. From, again, your discussion in vibrations, you've probably looked at these types of frequency response when dealing with suspensions on vehicles. That's probably maybe the first thing that comes to mind. But maybe many instruments that are also measuring instruments that are subject to a vibrational or a sinusoidal input are going to behave very differently, both in terms of their physical behavior and in terms of the readings that they give, sometimes as a function of the frequency of the input to them. And another example that's very common to this is audio system, hi-fi audio system. So the a speaker's response, for example, to an input signal, which is really a series of sinusoidal waves, is going to be very important for the performance of that system. So that in mind as we move forward. So for a closed loop transfer function, or closed loop system of the form that we had before, we're going to have something like this. Closed loop transfer function. Of our system. Our system, of course, is this guy that we had above right there. closed loop transfer function is, we're going to denote it as is DCL for closed loop. And so we're hitting that closed loop with our sinusoidal input, A sine omega t. And now I've done the block diagram algebra to simplify this significantly, and I'm in the S domain, I should point out. And I've got my output C of S. So let me be more consistent here and say that if I want to be in the S domain, this is what I'm going to have. So the whole question of the frequency response analysis is, what is C of S? And the remainder of this lecture is going to be to show we will show that the response of the system back in the time domain now, so in other words, the inverse Laplace transform of the C of S is also a sinusoidal function with a magnitude that amplifies the input magnitude by an amount m, which is itself going to be a function of omega. And because it's a sinusoidal output, it's going to be, that amplitude is going to be expressed as a sine wave at the same frequency as the input, plus a phase change that I'm going to call phi. Okay, so this is the point where magnitude amplification and phi of omega is the phase change, phase shift, we were going to call that. And this is the whole point of this analysis of this video, is to demonstrate that that's what we end up having and what the implications of that are. Okay. All right. So first of all, we know that C of S, based on the definition of the transfer function, is simply equal to the input, my sinusoidal input, times the closed loop transfer function, right? Which, given that I know that I'm dealing with an R of S equals A sine omega t, is going to be A omega. And of course, I could have done this exact same analysis by using A cos omega t as my input with no loss in generality here. As you know, the two are simply related by a shift, phase shift. All that times my closed loop transfer function. Okay, so yeah, so let's break that down into the poles of my input, which we've already looked at, and I'm going to switch back over to i's here since I did that for my Euler's function here. I should start with i's to begin with altogether and be consistent all the way through, but I'm going to try and stick with the i's from now on. All that times whatever my closed loop transfer function is. Now, I'm doing it this way because what we'll do next is a partial fraction expansion of this C of S function right there. And you recall how that works, right? We take the poles of the entire thing, and then we split it out into a sum of first order and second order components, and build up the entire frequency response in the S, or the entire response in the S domain first, and then we're going to take the inverse Laplace transform of that in a form that gives us, byte chunk inverse Laplace transform, if you will. Now, before blindly jumping into that, let's take a look at what this physically is going to mean, though, because that's going to be a key motivator for how we're going to analyze these systems. So G, the closed loop transfer function, we're going to assume that the system that we're dealing with in the first place is a stable system, right? So G, if it's a closed loop stable transfer function, it's going to have its own poles. Which means that the poles are all where? The left-hand side S-plane, of course. Okay, so let's put them, wherever they could be. I could have one off right there, which is going to come as a symmetric pair. I could have some poles that are on the x-axis, and of course you're experts right now at drawing the root locus plot. If, for example, these were my actual poles of the closed loop transfer function. And for my forcing function, this guy right there, I also have poles. I'm going to add on this same plot right there. And I've got one at minus I omega and one at plus I omega. So here we go. For whatever value of omega that I have, here's the first one. It's at plus I omega. And I have the composite one at minus I omega. This is my imaginary axis. And this is my real axis. As always, that's plain. So what do we know about this, right? So let's make that clear. These are the poles of the closed loop, and these are the poles of my input function. So what we know from the poles of G closed loop, if they're all on the left-hand side the way I've got them for the stable system, is that they cause the response to die off after a certain amount of time. So all the response of E of S, closed loop here, will die off if I wait long enough. And all that we're going to be left with, remember the settling time goes like 1 over tau omega n, and tau is the angle of the poles with respect to the negative x-axis. So for any positive value of tau, I'm going to have a finite settling time, if you will. Whereas for the two guys that are on the imaginary axis, tau is essentially 0, which means that my settling time is effectively infinite, meaning that the effect of the sinusoidal response in terms of poles and response is that it's going to outlast anything to the left of it. So if they die off, we are left with the response to the input only at steady state. If I wait long enough for all these guys' effect to die off and to basically become steady with the magnitude of my input, then the only thing that changes with respect to time, or can change with respect to time, are going to be the poles that I have that are right on the imaginary axis. So with this observation, that means that as I'm expanding this guy into partial fraction expansion, I don't have to worry so much about the roots of the closed loop transfer function. Right? The way we normally do that is I would expand G sub CL into a whole bunch of factors on the denominators, and then I would set that equal to A times I don't know, s minus the first root plus b times s minus the second root, or sorry, plus second root plus blah, blah, blah. And if I had a second order bit, I would be cs plus d divided by a denominator, that's another root, etc. And then to find the ABCD and so on, I would multiply by the root that corresponds to that particular guy. So in this case, it would be minus s1, and everything else would cancel except this, and I would be able to find a. The point here is that if I recognize that at any given time that response is not important, if that time is less than, is greater than the settling time, yes, these particular transfer function roots are going to affect the response only between time equals 0 and the time of the slowest of the roots of the closed loop transfer function. And for any time beyond that, they're really going to have no effect on the behavior of my system, except the amplitude of that having an effect on the overall amplitude of the response that it has to the input. So because of that, I'm not going to bother to do all that. I'm going to say, well, I'm only going to quantify the response C of S and later on C of T for when the time is greater than the slowest response of the poles of the closed loop transfer function. Does that make sense? So rewriting that, I guess what I'm saying is that C of S, which is equal to A omega G closed loop of S over S plus I omega, S minus I omega, writing that into partial fraction expansion. It's going to look like some constant K1. I used A's over there. I don't want to do this really because I do have an A in here already. So I'm going to use a different constant here so as to not confuse things. Right, I'm simply doing the partial fraction expansion of this system here. Plus K2 times my second root of my R of S, right? Plus, and now I've got the partial fraction expansion of the closed loop transfer function. But what I've just said is that these are all terms that die off, right? So they're going to be things like e to the minus t times omega, etc., something like that. So if t is large enough, then the term just goes away. It's gone. So all I'm left with is the response due to this K1 and K2. So we're going to solve this thing just by worrying about the K1 and K2. So, and that's going to give us the response of the system at steady state. So multiplying through just like we normally do with partial fraction expansion, that's going to mean that A times omega times G closed loop of S is equal to, I'm multiplying through by S plus I omega, S minus I omega, so that's going to be K1 times S minus I omega, because the plus cancels, plus K2 times S plus I omega now, because the S minus I omega cancels with the denominator on the other side. And that's what I need to solve here for my Laplace transform that I'm going to take the inverse Laplace transform of in order to solve this problem. And recall how we do this, again, partial fraction expansion. We're going to substitute in the values of each of the roots. So the first one is, let's say, I omega. This is going to give us A omega, GCL of S equals I omega is I omega here, is equal to K1 times I omega minus I omega. That's going to go away. Plus K2 times I omega plus I omega, which is 2 I omega. And so right off the bat, I got that K2 is equal to A the amplitude times g closed loop of I omega divided by 2I. That's my first constant. And it is a constant, right? Because for a given input that I'm putting on to this system, sinusoidal input, I am picking one frequency omega. So omega is really a constant for a given test, if you will. A is the amplitude of that sinusoidal input, and that's it. G of the closed loop transfer function is simply a function of this value of omega. So I'm evaluating the value of this function on a constant, so my output is going to be a constant. So this whole thing is a constant. Okay. All right. Similarly, doing the same thing at s equals to minus I omega, dot, 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 you're going to find that K1 is equal to minus A over 2I d closed loop at minus I omega. Again, a constant. Okay, same reason. So, putting that together, that means that output of my system is equal to A times omega times G of S divided by S plus I omega times S minus I omega, and here I'm forgetting my closed loop here, so I'm putting it down there. That's equal to minus A, I'm substituting for my G1, my K1 and my K2 now, A G closed loop of minus I omega divided by 2I times 1 over S plus I omega plus A times G closed loop. K2 is GCL of I omega divided by 2I times 1 over S minus I omega. Okay. So one more time, it's worth highlighting that these two guys, they're the only things that change with time. Components that will change with time when we take the inverse Laplace transform. So these two guys are simply going to get pulled out just like any constant would as I take the inverse Laplace transform. So these are, these are constant. For a given omega. Okay, and same with this. Okay, so we're in pretty good shape now, right? We're in good shape because we do have entries for the Laplace transform of these two fellows right there. That's our classic one. That's our exponential function. So let's take the inverse Laplace transform of C of S. Minus. And that's going to be equal to this fellow right there times the inverse Laplace transform of that. And the inverse Laplace transform of that is equal to e to the minus I omega t. And the inverse Laplace transform of that is equal to e to the plus I omega t. So putting it all together here, without writing more than I really need to, it's going to be equal to minus a times the value of my closed loop transfer function evaluated at minus I omega. And remember, we know how to do this, right? This would be my domain, and this would be my range. As we do our polar representation on the S-plane like we did last week in our phasor notation review. This is what I'm going to have. A G plus I omega divided by 2I times e to the plus I omega t. Okay, and this is equal to physical response of the system in the time domain now. So this is how the system responds in the time domain to the input R of t. And of course, if I'm dealing, say, with a crossover network of a speaker, and this is, the amplitude of the sound that I'm getting for a given input R of t, the electrical sinusoidal input going into the driver, then that sound is a real thing, right? It's a real physical system. So there's no imaginary component to that sound, which means that the C of t must be a real, number. I'm not going to get, an imaginary dB out of this thing. Just like if it represents a suspension, I'm not going to get an imaginary displacement that has no physical meaning. So this C of t must be real. Okay, so whatever imaginary component is associated with it, either from the functional relationship or this e to the I omega t, must come as a couple, and they must cancel out, is what I better hope is going to happen. So this is, let's call this guy equation 6, and let's look at what that means. Right, so that's going to look like something like this. Try like this red here. Go with black. Here's my imaginary axis. Here's my real axis. Okay, so after I plug in for a given value of I omega, then plus I omega is there. That's my domain, right? I'm going to take this value of I omega, I'm going to apply the function to it, and once I do that, I'm going to get some other number on the G plane and on the S plane. So let's say that I'm right there, G the I omega. That's the answer that I have. I better be on the left-hand side of things. And similarly, in order for this to be real, I'm going to have the complex conjugate of that G of I on the other side for minus I omega. And be right there. And they're going to come off as a complex pair. So I can express these complex pairs in a couple of ways, right? Okay, I can express G of I omega of minus I omega in two ways. The first one is as a complex pair, where G of I omega is equal to some real value A plus I times some imaginary value B, and the complex pair, the complex conjugate, is going to be the same A minus IB. So what that looks like is this here is going to be A or minus A, and this guy right there is going to be, or actually if I want to express as A and IB, this better be plus A. This is the actual value of A being a negative number, and this guy is plus B and this guy is minus B. Okay, And if I draw a ray joining the value of the complex conjugates to the origin, I can also express this as a phasor, which has an angle phi on the top one and an angle minus phi on the bottom one. And the magnitude of both of these guys is going to be the same. Let me call it m of omega here, and define what I mean by all these things here. M of omega simply represents the magnitude. Express that with the usual vertical bars of the closed loop function evaluated at plus I omega, okay, which is also equal to the magnitude of the closed loop transfer function evaluated at minus I omega. Okay, because again they're complex pairs, both of which are a squared plus b squared square root of. Okay, we got that from our discussion on polar representations last time, and that's what these m of omega represent. Okay, so it's not a separate function of omega, it's simply the amplitude of g at I omega is what we're representing here. And phi of omega, also a function of omega, are these angles here that I've shown. Phi is going to be the inverse tangent of this rise, which is b, also a function of omega, and this run, which is a of omega, just like that. And I've got one which is counterclockwise on top and one that is counterclockwise on the bottom of the same magnitude, right? Does that make sense? So this is my complex pair representation here. And my second way is in phasor notation. Having developed all this here, this is the way, if you haven't guessed yet, that's going to be a preferred way for these types of analysis, to say that g of I omega is equal to the magnitude of g at I omega, which we've already defined as m, times e to the, sorry, not minus, but plus I times phi of omega. So that's going to be equal to m of omega, now that I've done that, a positive number, times e to the I phi of omega. And so g at minus I omega is going to be a phasor of the exact same magnitude times e to the minus I at that same phase angle, negative phase angle. All right. So these two representations here, let's give them some equations number as well, because we're going to be using equation 7 and equation 8. Okay. And if we take these two equations, 7 and 8, and we substitute them back into 6, then we're going to have we're going to be in good shape for for having our time domain response for this system. So let's write that down. Substitute equations 7 and 8 into 6 to get time domain response. Okay, and we're going to have if t is equal to our new value of the function evaluated at I plus I omega and minus I omega. So C of t is equal to minus a times g closed loop evaluated at plus I omega, which is m omega. Sorry, not plus, but minus, right? Yeah, it's minus. The first one's minus. At minus I omega, which is this. So e to the minus I phi of omega divided by 2I multiplied by e to the minus I omega t, e to the minus I omega t. Now you see what's going to happen, right? I'm going to multiply the two e's together, and so therefore their exponents are going to add to each other. Similarly, for the other term, it's going to be a times m omega divided by 2I, e to the plus I phi times e to the plus I omega t. Okay, I'm going through the algebra fairly slowly here so as not to skip a step. And now I'm going to pull out some of the common factors out of this, starting with a, the amplitude of my input, times m omega, which is the amplification factor of my response, as we talked about before. And what I'm left with are e to the I omega t plus phi minus e to the minus I, that's actually these guys right there, omega t plus phi again, all that divided by 2I. Wow, okay, so it looks ugly at first glance until we remember equation, was it 4 from above? Or were all these equations that we started off with? Yeah, manipulations of Euler's identity, which gave us this nice equation 4 here. Okay, this is simply a manipulation of Euler's identity. And that's in exactly the same format as what our final answer is, where theta is this function of omega t. Specifically, it's omega t plus phi. Where are we? Omega t plus phi. That's the theta from equation 4. So compare to equation 4 with theta equal to omega t plus phi to get that c of t is equal to a times m omega times sine of omega t plus phi, or theta, from what we had above. Wow. Super cool, super simple result for the frequency response at steady state of a system subjected to a sinusoidal input. So the whole basis then, oh, and I should highlight also the fact that this phi, this phase angle, this shift, is itself a function of omega. And omega is a constant, right? For any given run, I've got 1 omega, and I'm letting the system reach a steady state, and I'm observing what the system does. And the whole basis of the frequency response analysis is to figure out what is that magnitude of the response or amplification of the input of the input amplitude, and what is the phase shift by which the response behaves with respect to that input. In other words, if I have a mass on a spring damper system that I'm subjecting to a sinusoidal input, if the input is moving up, it's possible that at that very same time the mass is moving down. So the phase of the response to a given input would be 180 degrees, for example. Okay, so that is the whole purpose of this frequency response analysis. So m magnitude as a function of omega, which is constant for a given value of frequency, represents the magnitude amplification of the input sinusoidal, tough word, sinusoidal of the input sinusoidal value, if you will. Value meaning its own amplitude. And phi of omega represents the shift in the response. And that's what we are going to, that's what we're going to spend all our time looking at the rest of our class here. I don't like that color either. So, for example, let's say I have an input, make that kind of light. R of t is my input. Nothing happens. In fact, I shouldn't say that because I'm not starting at time equals 0. I'm starting at time equals bigger than the slowest settling time of all my poles of G closed loop. But after that happens, my sinusoidal input, which has a magnitude A, I can represent this way. It's like this. Three nice little cycles. And my response, C, let's pick a completely different color. Let's say this, C of t, is going to have a magnitude, which is a function of the frequency omega, which is going to be, a function of the time period that I've got here. Could be bigger, could be less than the original A. This is my original A right there. So for the sake of making a nice sketch here, I'm going to make it smaller. This is m omega times A. And that's going to be over here, which is about here, the other side. And it doesn't start at the same place either. So I'm going to offset it by this much here. Stuff. That right, oops. Almost like art here. Okay. There we go. Something like this. So you see that there is a shift, and that would be the value of my phi omega. This is not the value of phi, but it's a function of phi, right? Phi would be 2 pi over that. So f of phi of omega. And the amplitude is a function of that. So in this particular case, my output lags the input at steady state. But if the red curve was shifted to the left sufficiently, it's possible that my phi would be negative, and then we would say that my response leads input. Okay, so this is what this is all about. We're going to need to determine what that m omega and what that phi of omega is. So the goal of frequency response analysis determine m of omega and phi of omega. This is what it's all about. And the way we're going to do that, is to look at a single x-axis where omega goes from very close to 0. The x-axis is plotting different values of omega now. We're going to go from very close to 0, and we're going to increase that frequency of excitation all the way to infinity, quote unquote. But because that's obviously a very large range, this is what we're interested in figuring out how the system behaves. As the frequency changes by that much. In order to make the visual representation of this result more easy to interpret, we're going to plot that changes in omega on a logarithmic scale. So it's going to allow us to move by decades instead of linearly, and it's going to make the graph so much more clear. And on that same scale of omega, so I would have, what I'm saying is I would have a plot of log omega, which is essentially, omega. And I'm going to do that same plot twice, same scale, same everything, right? It's the same x-axis both times. And on one of them, I'm going to have an amplitude. And on the other one, I'm going to have the phase. And so, my plot is going to do something. And if I then want to analyze the behavior of my system at a given frequency omega, once I've established this frequency response plot, I would pick that omega, which is on both of those intercepts, and I would know by how much my initial amplitude is magnified, and I would know by how much my initial signal either leads or lags, my response leads or lags the input signal. And that's the beauty of the system of the frequency response analysis. And we call these two plots right there. This is what we mean by Bode diagram or Bode plots. It's a plot of magnitude and amplitude. Magnitude and phase shift as a function of input frequency of oscillation. Voila! Now you know. The rest of the class, the rest of the course, we're going to spend figuring out how to sketch these Bode plots, these curves that represent the magnitude and phase shift for systems as a function of omega. Keep up your reading, and I will talk to you soon. Take care, everybody.